because he was in Mountain View in our headquarters for a couple of meetings. And actually right after this at 10 p.m. is your flight? 10:30. So he decided to stop by to give his presentation because there was a lot of interest. And then right after that has to fly back to Chicago. Overseas. Oh, you're extending your tour to the next office. Yeah. Yikes. So he's giving everything he got for us. Very appreciate it. And so I have to read it off because this is a long title. The first one is easy. Michael is a distinguished engineer here at Symantec, but also adjunct associate professor of computer science at the University of Chicago, and also has a long, long history with C++. But I will let him talk about it because he probably knows much more about this. So please join me in giving a warm welcome to Michael.
Okay, well, thank you for inviting me, Armin, and thank you all for coming. I notice when you're looking on the WebEx, it doesn't seems like there's a gap in the picture. Will that be in the recording and for everybody watching? Yeah, why don't you do that? I don't think there's anything really important in the upper right-hand corners of my slides, so you may be okay. But let me know if I need to reset the sharing or anything. And the slide is not advancing. Try this. There. Okay. I'm going to leave you to worry about that. Okay. So this talk is about memory in C++. And memory is a big thing in C++. And right? Is there anybody here who doesn't know that memory is a big thing in C++? Okay, you're all laughing, but when we finish this talk, you're going to leave and you say, wow, I never realized that memory was such a big deal in C++. Like, no matter how big a deal you think it is, it's a bigger one. But let's start at the beginning. The first rule that every C++ programmer learns is you create objects, at least those with dynamic lifetime, by calling new. And when you're done with the object, you need to release it by calling delete to avoid a memory leak. So the first thing I want to do is convince you both of those rules are wrong. Okay. And as of C++ 14, it's generally becoming regarded as best practice to never call new or delete. And after we do that, then we'll do things that are really interesting. So, first question is, what's wrong with new and delete? There are two answers that are sort of at least post-standardization C++ features. There are exceptions and threads. So the problem with exceptions is it makes the control flow of your program unpredictable. So God knows where you should put the delete statement. So here, if you look at the code on top, I allocate the object with a new A statement. I run some code, and then I delete the object. This isn't really a very good example because I never use the object that I created, but yeah, nevertheless, the code looks great, right? And you'd probably never notice anything wrong in a code review, but what could happen is if G throws an exception, then the object will never get deleted. Probably won't happen enough to cause any problem in QA, but finally, one time in production, right, there'll be some error condition that's hit repeatedly, and you end up leaking a lot of things. There's actually a time when the Toronto Stock Exchange went down because of a memory leak caused by an exception condition, right? So it had to do with like trading being stopped in one thing because of a limit on a certain circumstance, and they actually then had to shut down the entire exchange. So you can't ignore the fat tail for something like this. The other problem is threads also make memory management more indeterminate than you would like them to be. Because if you have an object that's shared between threads, you don't really know until runtime which is the last thread to use the object. So you can't safely put the delete anywhere in your code. By the way, how's this mic working? Good? Yeah, apparently it doesn't matter in here, but there are people listening on the WebEx. Good, perfect. So can we assure that the delete is never skipped? So are there any Java programmers in this room? There are 3 people brave enough to raise their hand. Okay. How many Java programmers are really in the room? Yeah, I got a few more that time. Okay. So a Java programmer would say this is a defect in the language, right? They'd say, why didn't we just use finally? Now, they'd also say it's a defect in the language because why aren't we garbage collected? Well, we'll come to that one later, right? So here you could imagine we'll create a finally statement for the delete. It's guaranteed that we would delete the object. There, of course, is only one big problem, which there is no finally statement in C++. Okay, and that's actually a feature, not a bug. Does anyone know why there's no finally statement in C++? Right. You have destructors, which you don't have in Java. You also allow class objects on the stack, which you don't do in most other languages either. And there's a name for the idiom of using a destructor to control the lifetime of a resource. Does anybody know what that is? RAII. Right. So RAII is short for resource acquisition is initialization, right? So I always have to look that up when I teach my class because, it's ridiculous, but you can remember RAII. All right. So C++ 11 has a smart pointer template called unique pointer, whose destructor deletes the object that it points to. Okay, and here's a simple way to fix the memory leak. Okay, instead of having new A instead of storing the pointer to the new A in a raw pointer, store it in a unique pointer. And unique pointer, when the unique pointer goes away, it'll delete the object. And that unique pointer is going away whether you leave F via normal return or via an exception, right? By the way, before there was unique pointer, there was something in C++ 98 that did the same thing called auto pointer. Anyone know what happened to auto pointer? Yeah. Right. Auto pointer is fundamentally broken, and in fact, the brokenness of auto pointer is what I think led people to add move semantics to C++ 11 to fix it. So if any of your old code has auto pointers, you should change them to unique pointers. And there's a nice Clang tool that will automatically fix all the auto pointers in your program. You can make use of that. Okay. If you want to use a unique pointer that points to an array, you can say unique pointer angle brackets A square bracket, because for raw pointers, you'd use an A star for both an array and an A object, but for smart pointers, you definitely don't want to do that. So a unique pointer says, I have sole ownership of this object. I'm the unique owner of the object, so when I don't need it anymore, it's done. It's safe to delete. There's also a shared pointer class, which is a reference counted smart pointer, and it says I can have shared ownership with someone else. So this means that object is deleted when its last shared pointer goes away. And this is very nice, say, when you have multiple threads owning the same object. It'll know when the last thread using the object goes away and deletes the object. Interestingly, there is no shared pointer for arrays. Okay. You know the reason for that? It's because we're idiots on the standard committee, right? There is no reason for that. So this is corrected in the library fundamentals technical specification, which will eventually end up in C++ 17. Until then, you can use a custom deleter. Say Google it. There's a boost scoped array class. You can do your own class. The deleter associated with the smart pointer is actually very powerful and allows you to actually do some memory management that you might think you wouldn't, right? I'll just say one example of it, right? Besides the array deletion thing. If you've done Windows programming, you may know that memory allocated in one shared module should only be deleted by that same shared module because each DLL has its own heap in most circumstances. The built-in deleter in shared pointer gets that right for you all the time. So whichever DLL, the last reference to the object, goes away, the shared pointer will assure that it's been deleted by the allocating DLL. So you'll probably fix some subtle bugs in your code to do that. What's the best practice here, right? Is calling delete is just asking for trouble, right? So everybody here probably knows effective C++. So the effective C++ book is a collection of all the sort of agreed on C++ best practices. And it says, store nude objects in smart pointers and do it in the standalone statement. And this gets rid of the need to call delete. There's an interesting proposal in the spirit of this best practice by Walter Brown called a proposal for the world's dumbest smart pointer. Apparently, it took us 3 revisions to get it right. And I actually plan to contact Walter later this week to get a version 4 in the next mailing. So, right, C++ is a complicated language. When it takes the standard committee 4 tries to get the world's dumbest smart pointer. So what he did is he adds an observer pointer that acts just like a raw pointer. It's just a note to you if any ownership of the object. And that way, the pointer you work with always explains what your responsibility for the object is. And that was also in the library fundamentals. So, okay, now you've kind of moved a little on a par with Java, right? You don't need to call delete. Let's see if we can move ahead. So, why get rid of new? All right. So even garbage collected languages use it. So the problem is that calls to new violate that best practice. Okay? So that can get you in trouble, right? So here, if I say G of new A, that can leak memory. How can it leak memory? Yeah? It say G is responsible for deleting. Aha! Right? Exceptions make control flow almost completely unpredictable. Yes. Well, references and pointers have much different semantics. For example, a reference can never be null. A reference can't be rebound to reference a different object, but a pointer can be. Well, sure you can. All the observer pointer does is it says, I have no ownership of what I'm pointing to. Right? So it's just something that explains to the person who's looking at the code, am I responsible for deleting this object? Right? So the vast majority of pointers are really observers, and pointer assignments and null pointers are common for those. So if the first new way works and the second new way fails, then G will never be called. Hey, by the way, which is the first new way and which is the second new way? Right, it's undefined, right? Heard a lot of people say that, right? Order of evaluations of arguments in C++ is not specified in any way, but one of them will be run first, the other will be run second, and if the second one to run throws an exception, G will never be called and no one will delete the first A object created, right? Just try to find this in debugging, right? So the real point is it's a mistake to ever have an owning raw pointer visible, right? So let's fix the code, and this fix is actually wrong. So let me that's interesting. It won't let me go to anything other than what I'm sharing. So can we just get the screen back up? Is there any hotkey to move it back to projecting? Oh, that didn't do anything. No, I have slightly grayed out windows here. We don't need slides, right? Okay. There it is. Now it gave me the WebEx back. Okay, I'll just explain what's wrong with the code, because C++ is complicated, but PowerPoint is more complicated. Okay, it also decided to stop mirroring. Okay. This is what's blocking your screen. I get rid of that. Okay. So, make unique and make shared will create an object and return an owning pointer. So, if you use make shared or make unique to create your object, you're guaranteed it's going to return a pointer that's ready to manage the object as soon as you need it. This code is actually wrong. And what's wrong with it is that if you remember the best practice, it said in a standalone statement, right? So I don't want to release the object without an owning pointer, right? So you should make unique then the make unique on its own line for each of them and then call G on the result of releasing them. So in the C++11 edition of effective C++, it says prefer stood make unique and stood make shared to direct use of new. So whenever you create an object, use make unique to create the object and return you a unique pointer to it, and make shared to return you a shared pointer to the object. So there are some further improvements that we could make. Okay, so really, I don't want to call release. What does release do on a smart pointer is it gives you the raw pointer. And we probably don't want to pass, say, an owning raw pointer. So we should probably modify G to take two unique pointers. So now we really can call unique, make unique. And that, okay. But interestingly, if P1 is a unique pointer and P2 is a unique pointer, I cannot call G of P1 comma P2, right? And the reason for that is kind of a like subtle impact of C++ move semantics, right? If I say G of unique pointer of T, unique pointer of G of make unique T, make unique of T, these are temporary. So they're going to go away, and G will end up being the sole owner of the objects, right? C++ move semantics says the compiler will move out of a temporary. But if I stored P1 and P2, the unique pointers, and then I said G of P1 comma P2, well, then G would have unique ownership to the objects, and P1 and P2 would also have unique ownerships of the objects, and right, then it's not so unique anymore, right? So if we really wanted to have P1 and P2 give up control of the object, pass it to G, I say G of move of P1 and move of P2. And move basically turns an expression into temporary so that C++ will move from it and assume that the old value of P1 goes away. Okay. So when I talk in the abstract that having a new, getting rid of new and delete in C++, who thought I was talking about garbage collection? Right. So this is not standard practice in C++, but it's often useful, which is C++ is a perfectly good garbage collected language if you want it to be. Okay. So there's some minimal support for garbage collection in standard. I'm not going to talk too much about it because the support in the standard is pretty minimal. But there's a paper called Garbage Collection, the next C++ standard, that talks about it. And the support basically says C++ is not allowed to do anything that would fool a garbage collector. right? Like if you ever use the XOR trick for a doubly linked list to save space, look it up, because it's one of these things. Like first you're like, wow, how could, it never occurred to me that you could do it, and subsequently, right, thinking has evolved to why would you ever want to do it? But a garbage collector won't understand two pointers XORed together, right? So basically, if you ever hide a pointer, the language is now allowed to automatically delete what it points to. Okay. However, no garbage collection mechanism is provided. It simply says that it's allowed. And if you want to enable garbage collection, you can use a third-party garbage collection library like the Bone Collector, and then you never need to free an object. And if you've never played with them, they work really, really well. Okay, so experimenting with garbage collection in C++ is really worthwhile. The first reaction people have when they hear about garbage collecting C++ is it's not possible because C++ is not a type-safe language, right? So it's perfectly okay to store a pointer in an integer, right? Or XOR pointers, things like that, okay? So most of these behaviors were turned into undefined behavior in C++11 to make sure that conforming programs could be garbage collected, but storing pointers in integers is still possible, yes. Performance is great, right? Garbage collection is probably faster than putting manual freeze in your code because a garbage collector frees a bunch of objects at once. All the manual memory management takes a lot of time freeing the objects one at a time, and then, say, in the case of a shared pointer and multiple threads, every time you adjust the reference count, you have to do some kind of synchronizing operation to atomically adjust the reference count. So the speed of garbage collection is great. The penalty that's paid tends to be more in the area of space usage because garbage collectors, wait every so often and then do a collection where manual freeing frees an object as soon as you're done. So typically a garbage collected program is the same speed as a manually managed program, probably uses 50 or 60% more heap. Good. Well, usually garbage collectors have some efficient method for doing bulk deletes. They also don't have any of the cost of, maintaining reference counts or program logic for keeping track of what's in use and stuff like that. So, sometimes it's faster, sometimes it's slower, but on balance, it's very performant. Yeah. Well, let's look at some upcoming slides, and you had something. Well, it varies. as I said, sometimes it's faster, sometimes it's slower. Ben Zorn's PhD thesis did a lot of benchmarking on real-world apps, and it's an old paper, but it's still probably pretty accurate on it. So, C++, what they typically do is treat every word of an object as if it were a pointer. And amazingly, this is performant. And why? It's because computers scan memory very, very fast, right? And typically, you can reject a word just by seeing if it points to the region of memory that contains your heap. So typically, like 3 or 4 machine instructions can be used to reject all non-pointers. So here are some links on it. And again, I'd recommend try it on your own code and see how it works for you. There's all kinds of amazing optimizations. There are also non-conservative precise collectors. There are move collectors. There's all sorts of things. I could give a whole talk on garbage collection. I think my standards proposal on garbage collection had like 80 pages of wording. It's a big and interesting topic. So, yeah, so I just go to Hans Bohm's site and explore. I think it's worthwhile doing, but I won't spend more time on it now. Yes? It's possible, but frankly, it's a bad idea. So if you look, you know, like those buttons on elevators to close the door, and they don't actually do anything. They're not wired. Their whole point is to give you something to press, right? Right, so if you're in Java and you call system.gc.collect, it does nothing. Right, in Java 1, it ran a collection, but over time, it was realized that like manually triggering a collection is probably a bad idea. Well, look, think about it like the register declaration, which is in C++. If you disable optimization, right, register declarations are respected. But if you turn on optimizations, register declarations are ignored because they make programs slower, right? So some things just should be done by the compiler. Let's talk a little about what is memory in C++. So perhaps the biggest addition in recent years in C++ is support for standardized concurrency. So this is multi-threading to run multiple tasks in parallel in a process. And there are synchronization primitives in a memory model to allow different threads to work safely with the same data. And the interaction of threads and memory comes up again and again. Okay, so why is concurrency the big addition to C++ recently? Well, the reason is like the dirty secret of computers is, you know, basically they haven't gotten any faster in the last decade. So 2005, Pentium 4 HT ran at 3.8 gigahertz. Okay? Probably none of you have a computer that runs at 3.8 gigahertz. Yeah. It's not fully correct, but because Pentium 4s hit these super long pipelines, whereas because they were really designed to do video decoding, right? Whereas modern processors have shorter pipelines that spill less. But the fact is, a modern core is just not much faster, if any, than a core was 10 years ago. Yes? There are scenarios, but fundamentally, for just running code, cores stop getting faster. The real gain, and part of the point of it is you increase clock speed, the amount of heat you produce and energy you consume goes way up. And you consider a high-end desktop or server CPU dissipates well over 100 watts in a cubic centimeter. Well, an incandescent light bulb dissipates 100 watts in 75 cubic centimeters, and just try grabbing one, right? That's a lot of heat to dissipate in a small space. Right. So why isn't everybody sticking with their 10-year-old computers? Well, it's because while individual cores have not really gotten faster, the continued progression of Moore's law means today's computers have many cores to run computations in parallel. So this cell phone has 4 cores in it. My desktop computer at home has 20 cores. So those of you who work Symantec like me, I know there are a lot of you here, you'll be surprised like what kind of desktop you get to negotiate with your boss. That's just a pointer here. Okay. And with hyper-threading, you have like 24 to 48 cores is not on. So C++ didn't have any notion of multi-threading until C++ 11 came out. And C++ programmers had to end up using OS-provided multi-threading libraries like P-threads and Win32 threads, and this isn't acceptable. And it's not only because the lack of language support is clumsy. In fact, threads cannot be implemented without language support. So this is a great paper by Hans Bohm, which has some slides and not the right order, so I'll just mention this as here's some good references for C++ concurrency. So why can't you do threads as a library? Well, the reason, again, is memory. Okay? You can ignore the next few slides. Bizarre behavior that was outlawed in C++ 11, but this will help explain the memory model in C++ 11. So here's a interesting puzzle. If X and Y are multiples that are 0, when thread 1 and thread 2 have completed, what can you say R2? What? You are correct, but it doesn't seem correct because logically you can't have both R1 and R2 be 0. But in practice, right, the compiler may reorder the statements because it has no understanding of threads. So it doesn't matter in a given thread which order the assignments take place end up with them both 0, even though that has a visible effect on program execution. One comment is, right, the pthread standard says this is illegal, but C++ didn't have threads, so compiler vendors didn't care about whether they made the pthread standard illegal. Okay, here's another interesting example. Okay, so until C++ 11, here I have count as a global variable, and I run through a loop and count the number of elements in the linked list, beginning with Q. If Q is null, right, the count should be 0. What could another thread see the count as? What? Not any, probably not any value. What? Well, okay, but let's not be right. I mean, in point of fact, G++02, other threads may see this as not count as non-zero. You got it, right? So one problem with code operation is that the branches are expensive because they spill your pipeline. So compiler may reasonably assume that your loop is run at least once. And then if it turns out that the condition fails, it could undo the action of running the loop the first time. So in fact, it's likely that other threads will see the count as 1 at some point in this due to speculative execution of the first time through the loop. And in fact, GCC-02 reproduces this behavior before C++ 11. And that's a, 02 is the realistic optimization level. It's not the tuned to the benchmarks with crazy optimizations you would never do in real life. It's just normal optimized code. Yes. That's true, but usually incrementing an atomic type, or not an atomic type, but like a word type or something like that, from 0 to 1, or honestly even a 64-bit number on a 32-bit machine from 0 to 1. You're never going to change more than one word at a time. So that one's unlikely in practice, where this actually occurs in practice. So this is kind of a notion of what does memory mean between threads. And one thing we're seeing is different threads may not agree on the content of memory. Here's another example. So here's some reasonable looking code. Thread 1 creates a new A object and stores it in little a. And thread 2 calls a method on little a, but only if something has been stored in it. Is that code correct? Why not? Then A will be null, and it won't. What? Well, no, global variables are initialized to null, so that's not a problem with the code. Okay, in theory, the assignment may not be not atomic, but that would be one weird architecture. So this is fundamentally broken code, and in fact, you should never do it on any architecture. Well, let's look at the code. It says new A, so A is going to be constructed, and then its address will be assigned to little a. So maybe you're on the right track, but you have to justify that statement a little more. Because if you look at the code, clearly the assignment cannot be done first. It's not a compiler issue. This is a what is memory issue in hardware. Okay? So the answer is writes to memory made on one processor may not be seen in the same order on another processor, right? So on processor 1, in fact, A will be constructed before its address is assigned to the pointer. But when processor 2 observes memory, it may see little a updated before it sees big A constructed. All right? This kind of technique allows microprocessors designers to use all sorts of great hardware techniques to improve performance, right? As compiler writers, we always go to the microprocessor people and say, yeah, please don't do all this crazy shit because it makes, it very difficult to write correct code. And they come to us and say, well, we'll stop doing this, once you don't let compilers do code reordering and stuff like that either. So, and then we're like, well, no, we get terrible performance, right? Right. So the fundamental problem here is that there's no guarantee that the order of memory modifications seen in one thread is the same as that seen in another thread, so the V-table may not be initialized, and you'll have a one-time in a million crash. Great. Yes? Yeah, the compiler could, but there's not really okay, I'll grant you that, but even if the compiler doesn't reorder it, the concept of what memory means in hardware can also cause this to crash. Okay, so modern processors use weak consistency, and what this basically says is that you don't see memory consistently between other processes unless you explicitly introduce some kind of synchronization operation that will flush the caches. Okay? So if the language doesn't have a notion of synchronizing memory, it's very difficult to use any kind of memory shared between threads. Typically, this was addressed non-portably by vendor-specific synchronization extensions to C++. Okay. C++11 introduced, by the way, why is this so important? The reason this is so important is processors are very fast today, even if they haven't gotten faster in the last 10 years. Memory is very slow. Okay? So if you actually have to go out to the authoritative memory every time you want to read data, right, you're going to have each instruction will take like 100 clock cycles, right? And then, you know, your program will be terrible, right? So all processors have caches on them to store like kind of a local replica of main memory. But as the different processors use the memory, those things can diverge. So you need cache coherency protocols to prevent conflicts from arising. But that does create the potential for different processors' view of memory to get out of sync, and supports the idea of generating hardware, having hardware use weak consistency models, because otherwise it's almost impossible to keep in sync. x86 is a pretty strong memory ordering, so you know, things could be worse. Okay. It also means your x86 program, if you move it to ARM or something like that, may not work anymore. So how's this fixed in C++11? And there's a very complicated definition of the memory model in C++11, but the catchphrase version of it is sequential consistency in the absence of race conditions. Okay, so what this does is it means that if data is shared between threads, you can never access it except within a lock or through an atomic operation, right? It's never, ever safe to use data that's shared between threads without using synchronized operations, right? Herb Sutter is a nice lecture on atomic that I have a link to there. Okay, so what are some simple best practices to keep you from getting in trouble with your memory model in C++? First is sharing data between threads is really bad thing to do. Okay, so it's always a last resort. Okay, don't use shared variables unless you really, really need to. When you do share data between threads, always use locks or atomics to ensure that both threads have a coherent view of the shared data. Here's a great article by our from Communications of the ACM called "You Don't Know Jack About Shared Variables or Memory Models." Right? Data races are evil. And basically, he lists a whole bunch of examples of where code obviously looks like it would be safe to use this shared variable, right, without a lock or an atomic in some other thread, and he shows why it could give wildly wrong answers, right? So literally never make an exception to this rule. Don't say, I'm just building an approximate counter, so, you know, I'll just do a non-atomic increment, right? You can get the counter will end up as being 1 when it should have been 1 billion. And that can really happen, right? You know, it's good to read this to put the fear of God in you. Okay. So there's another interesting aspect to memory in C++, and actually in any language, because but that it's important to understand if you're working with memory. So this is understanding the effects of caches on your program. So as I mentioned earlier, accessing main memory can take a processor hundreds of cycles. So therefore, processors use high-speed caches to maintain local copies of data. If another processor needs to write that memory, it'll need to force the original processor to flush or invalidate any cache objects, copies of the memory. Okay? So when data is moved from memory to cache, enough data is always moved to fill a cache line, right? So the idea here is if I access this location in memory, I'm likely to access nearby memory locations as well, right? So, you know, for example, if I'm reading machine code, I'm going to execute this instruction, then the next instruction, then the next instruction. Or if I'm reading a field of an object, I'm likely to read other fields of the same object as well. So the size of a cache line varies by processor, but a typical size would be 32 bytes. In the old days, you know, 128 bytes were more common, but they've gotten a little shorter. So as a result, if two processors within 32 bytes of each other, they're constantly forcing each other to invalidate their cache. So this is known as false sharing. You have two variables that appear to be independent of each other, and your program will work correctly, but every instruction will take hundreds of cycles to run instead of, you know, single-digit cycles to run, because they're both modifying data in the same cache line, and processors just check if the cache line was modified, right? So here I'm not going to try to switch to the code because we had that experience already, but I used to, by the way, have an artificial example of like how slow false sharing can make your program. And right, everyone believed that, like, yeah, this is like a computer scientist giving some theoretical example of no interest, right? So last year when I was teaching C++, I gave a common question, which was create a distributed method counter, all right? Which is a very, very common thing to do, creating distributed counters, because you'd like each thread to maintain its own count and then periodically having them update a central one, because otherwise you have to get a lock or atomic every time you bump the count. All right? So one of my students had an array of numbers for their counts, and each thread bumped its own number. This program ran a tenth as fast as it should have run because he thought each thread hit its own counter, and from a program semantics point of view, it did, but from a performance point of view, every thread hit the same counter, because every time they updated their counter, they modified the same cache line holding all the other counters, so all the other threads had to reload the cache line. This coupling of seemingly independent variables that reside on the same cache line is known as false sharing. Well, there's going to be a slide on cache-conscious programming that gives best practice. Then I'll come back to your question because it's a good question, and the answers will also. So the code just to put space between all of the counters. In fact, the program runs 15 times faster, right? Programming the cache is critical to writing high-performance code. Interestingly, on my student's laptop, adding the cache had no effect. Why? Because on his single-socket laptop, all of the cores were sharing the same cache, right? So it depends on your. So this is insidious because developers use laptops and then right at work, right? You know, I work on big data systems, admittedly not in C++ right now, but we have like millions and millions of dollars worth of computers on these big iron servers, and you don't really know that your programs are running a quarter as fast as they should run because your own benchmarking was good, right? And then you've wasted millions and millions of dollars. All right? So this is a good illustration of why following best practice, like putting independent variables on distinct cache lines, is important, even if your own benchmarks aren't showing it. Here's another issue with caches that's important in your programming to memory. So one thing about caches is they need to be really, really, really fast. So if there's some complex caching algorithm, it's not going to speed things up, right? So typically, every region of memory can only be mapped to a single cache line, or maybe two. Or okay, so these are called direct mapped caches. So typically, the way they work is, say, like bits 16 through 7 of of an address are used to determine which cache line you're in. Okay, so not understanding direct map caches can have dire consequences. So here's an example. It's actually exposed in Ben Zorn's doctoral thesis, which I mentioned earlier. So is anyone familiar with GhostScript? Yeah, a lot of people are. More people admit to knowing GhostScript than admit to writing Java code in this room. You know, it's okay. I'm actually converting a bunch of C++ code at work to a pure Java stack, right? Right. One should never be a bigot. Always use the right tool for the job. But anyway, GhostScript was written by Peter Deutsch. Now, an important comment here, Peter Deutsch is probably the #1 memory management expert in the world when he wrote this. Okay, right? He's well known for the Deutsch-Shipman Smalltalk compiler, which was the first high-performance Smalltalk implementation. Smalltalk performance is all about memory management. Okay, so he used a custom allocator. Who remembers this from last quarter, by the way? Good, everybody. All right, I'll talk a little about the algorithm later, maybe, but the general point is it's it's a page-based allocator. So it had a big linked list of free pages. And the first word of each free page was a link to the next chunk of free pages. So that's, and the algorithm is super, super efficient as an example of a bebop collector, which I'll come back to later, actually. So later, and Ben Zorn said, what happens if you replace memory managers and programs with different allocators or garbage collecting allocators or things like that? It found out that GhostScript's memory manager was actually slowing it down by 30%, right? This is the world's best memory management expert. Created a program that was way slower than it would have been with libcmalloc. Okay, so people investigated this, and this isn't published in the paper. So this is like some secret folk knowledge that I'm sharing with you. Everyone raised their no. So anyway, the point is, Ben Zorn tested this on a machine with a direct map cache, right? So this means the first word of each page got mapped to the same cache line on the processor because of the direct mapping. And guess what? Basically, that meant the program didn't benefit from having a cache when it walked the page free. Okay? So GhostScript was spending about a third of its time in cache miss from walking the page free list. So why didn't Peter Deutsch know this? Well, he's about as smart as they come, but direct map caches hadn't been invented yet. Right, so, somehow he didn't optimize the code for computers that don't exist yet. All right, so we're going to come back to this in a minute, but like over-tuning your memory management increases the brittleness, right? If you just used the standard allocator, this program might have been a little slower, but it couldn't be broken by a change in processor architecture because the standard memory manager would be upgraded. And that. So here are some rules from Herlihy and Shavit's book on multiprocessor programming for best practices around programming the cache. All right? So first one we've already mentioned are fields that are accessed aligned and padded so that they end up on cache lines. Another one is keep data that you mainly just read separate from data that you modify a lot, because if data that never changes is on the same cache line as data that changes a lot, you'll have to keep rereading the data that never changes because some other thread has modified something in its cache line. When possible, split an object into thread local pieces, right? So you have less conflicts between multiple threads, right? This is the rule of trying not to share memory threads whenever you can avoid it. So a counter should always be split into an array of counters, one per, each one residing on a different cache line. Okay, and that'll avoid an update to your counter invalidating the cache for other ones. So we illustrated the effect on performance that has. Now, if a lock protects data that's frequently modified, then keep the lock and the data on distinct cache lines. So the threads trying to acquire the lock don't interfere with the lock holder's access to the data. And if a lock protects data that's frequently the lock and the data on the same cache line, so that acquiring the lock will also load the data into memory for you. So now I'm going to come back to your question, which is basically, does that mean you always want stuff on different cache lines? No. Right? It really depends on the data access patterns of your program. Right? Cache lines are long for a reason, because you want to exploit locality of reference. So in your own code, and if you're writing a library like OpenMP or things like that, you need to actually think about data access patterns and then decide what's the best way to leverage the cache for that. If a class or struct contains a large chunk of data whose size is divisible by a high power of 2, consider separating it out of the class and holding it with a unique pointer, right? That may not look like a pointer, but it is, to avoid the ghost script problem. And modern profiling tools actually report on things like cache misses and contention and stuff like that. So use those. All right, so if those examples don't convince you that understanding memory is important in practice, let's look at a case study. It's from a friend of mine, and he started a company doing XML security appliances that he subsequently did a highly successful sale of to IBM, right? And every step of his business progress was determined by his switch in memory management strategy. Okay, so first, how could we fix size? So let's say we're only allocating 32-byte objects, right? So C++ lets you do things like class-specific allocators, right, that could be optimized for knowing what the size of that class is. Well, so what we'll do is take each 4,096-byte page, divide it into 128 32-byte objects, put a pointer to the next one in each. So now we have a linked list of 128 32-byte objects. And now allocate and deallocate the 32-byte objects from the list by pushing and popping. This is fewer than a dozen instructions versus hundreds of instructions in a conventional allocator, and lock appropriately for thread safety. For those of you who wanted to do our homework exercise here. So allocating an object is very, very fast, right? Just take what used to be the first object on the list, pull it off, and make sure the list head points to the new first object on the list. Okay? This is an efficient high-speed allocator, and you often see it used in class-specific allocators. Okay. So my friend wrote that allocator for his class, did that, and it appeared to speed up his program considerably. Went to market, and his customers reported that the application became slow as the number of threads increased into the hundreds, right? Like, you ever worked on a product and, work well in your kind of small-scale testing, and then you sell it to a big company, and they run it under like a really big load that you never anticipate and stuff like that. And the program became extremely slow. Okay. So what went wrong? Does anyone have a guess? Right, that looks like a fast allocator. Why is it a slow allocator when you have lots of threads? I hear a lot of mumbling now. Yeah. No, it's nothing we've seen before. Well, yeah, you're definitely locking. That's true. There's contention for the lock, but the lock's apparently only held for a few, like literally 2 instructions. So you'd think that wouldn't really be bad. But it is bad, right? Right? Why is that bad? Yeah? No, it's not something we discussed before. What? No, so here's the problem. Even though the lock only protected a tiny region of code, so you'd think it would be performant, what would happen is if your thread is trying to allocate on the list, and during those like few instructions, it happened to lose its time slice. Then it's not just locking for 2 instructions. It might be locking for 2 instructions, as all of the other threads, 100 threads, try to run before it gets back to the thread that holds the lock. So this didn't show up when the device was like only processing, say, like 10 open sessions at once. But when it was processing hundreds of open sessions at once, right, this loss of time slice issue ended up gating performance. And that was not acceptable. Okay, let's talk a little about atomics in C++, right? So sometimes you just want a variable that you can do simple things with for multiple threads. Too heavy for that. C++11 has a library of atomic types that can be shared between threads, and more importantly, processors actually have atomic instructions that these types can leverage, right? So here's an example of an atomic counter, right? So so basically, the atomic counter lets you increment it. You get the value out of a float. You put a value in it with store, and so forth, and it'll leverage the processor's ability to do that. So with the idea of atomics, many of you have probably seen this, but it's a good thing to see. Can we make a thread-safe linked list without locks? So if we think about what it takes to make a thread-safe linked list, it looks like we need a lock because we have to do a couple of things here, right? We have to update the head to point to B, okay? And at the same time, we have to pull A off the linked list. So that requires 2 different things. Looks like a race condition, right? So there's a clever way to do this atomically. So C++11 has an atomic compare and exchange command that does a swap, but only if the target location is the value that we expect. So then our update would fail if the head was no longer pointing to A, right? So using a compare and swap seems to do the trick for us. Okay, emphasis on the word seems here. So the problem is, what if some other thread does 2 pops in one push during the critical section unchanged? Then my compare and swap to update the head will think it's okay to update the head because it says, ooh, the head's still pointing to A, no one else futzed with the list, right? But of course, someone else did futz with the list, and we have a wild pointer. Okay. Anybody tell me what the solution to this is? You got it, right? So you are smarter than AMD, right? So, right, has anybody ever wondered why there's a single 64-bit instruction on x86? It's the compare and swap instruction. Okay. So what we'll do is we'll add a list operation counter to the head that's incremented every time the list is modified, and we'll atomically update both the list pointer and the list counter with a 64-bit compare and swap on my 32-bit program, okay? As you recall, Intel was pushing the Itanium in their move to 64 bits until eventually AMD came up with a 64-bit x86 architecture, right? So they said, we're looking at what they needed to add 64-bit instructions for, and they said, oh, we don't need to add a compare and swap because there already is a 64-bit compare and swap. Thank you, Intel. Right? But of course, if you have a 64-bit program and you want to make a lock-free list, you need a 128-bit compare and swap. So you can update both the list pointer and the list operations counter. So subsequently, that was added. But if you want to be super safe, check the CPU status word to see if it supports compare and swap, and really your C++ library will check that for you. So this is much better. It's somewhat faster than a lock, but the real thing that makes it faster is that if the thread loses its quantum, no other thread is blocked from operating because there are no locks. Now, when the thread gets its quantum back, the compare and swap will fail, and it'll just try again. Right? Because the compare and swap will say, yeah, someone futzed with the list. I didn't succeed. Let me retry. So this is efficient on the x86 architectures in Spark. Interestingly, it's not efficient on PowerPC and Itanium for all you Itanium programmers here. What do they do? Well, they have something called link, load, and store conditional, where the load places a reservation on a memory location, and a store conditional will only write if nobody has futzed with that memory location since you did the load, right? And that's actually exactly what we want here. How do you make your C++ code portable? Well, C++ lets you check which atomics are lock-free on your particular architecture. So just query if compare and exchange is lock-free to see which is the version you want. Okay. So my friend switched to using, remember, compare and exchange is good on Spark. Customers were happy with the performance. Things look good. But, right, there's always a twist. So the customers started to experience intermittent crashes due to allocator corruptions, like same object being doubly allocated and things like that. It was virtually impossible to debug. Okay? In fact, he ran 100 threads doing only list operations on his box for hours between failures. What could go wrong? Any idea? This guy's the smartest person I know, and right, you know, he was mystified. Hey, here's the problem. Okay, so Solaris interrupt handlers, right? So Spark is a register-rich architecture, so it's expensive to save all the registers in your interrupt handler. Okay, so 32-bit Spark for registers only save the bottom 32 bits because 32-bit programs use the bottom 32 bits of a register. Okay, well, because we need a 64-bit compare and swap, timer interrupts that would once in a great while occur during the section corrupted the compare and exchange. Okay, like, how many of you guessed that that was the problem? But I load the proposed new value of the head, then I do the compare and exchange. So what if my proposed new value of the head got modified before I do the compare and exchange? Right, so the compare and exchange is an atomic operation, but the pre-work for it assumes that the registers maintain their values, right? Absolutely, right? It's clearly documented. If you read all the Solaris documentation, which registers have all 64 bits preserved during an interrupt, right? So what he had to do was modify his code to only use the 64-bit save registers for the operation, right? Well, this was G++ and did some inline assembler, right? I mean, one of the great things about C++ is you can put in the machine language that you need, right? So, yeah, here's if anybody doesn't know the first rule of optimization, right? Right. In fact, if it's the only thing you take out of this lecture, it's good. The first rule of optimization is don't. Okay? Right. Right. It's so easy to get something wrong by doing some tricky, brittle optimization. So these techniques are powerful, but only used where justified. And we'll come back to that question, but the story isn't done. Okay? IBM bought the company, and right, everything IBM does is big. So instead of being on a, little appliance, now these are massive XMP network security appliances, and it started to exhibit performance problems again. So the point is, even though the compare and exchange doesn't acquire a software lock, it still has to lock the memory bus to do things atomically, and that's expensive as the number of processors went up, right? Like if you're a machine code geek like me, look at how the Windows interlocked exchange primitive works. You'll be surprised to know that it does not actually do an atomic exchange, even though x86 has one, for reasons like this. So since they no longer needed many more threads than processors because they had like 64 cores on the box, they went back to the original lock-based operation from square one and came full circle. So should you do a class-specific allocator? Well, here's some questions. You really want to pollute your class with deep assumptions about the hardware and operating system. You want to update it every time there's a new OS rev or a change in usage pattern. Right? If you had done a class-specific allocator like this before threading, your program would have become silently thread unsafe. So on the one hand, the answer, but yeah, so a successful thing without usable products, right? Section of code. So use it only if you're brutally honest that the costs of maintaining your code throughout this are justified. And this illustrates the real power and danger of C++, right? Which is, most languages say features that are misused more than they're used are removed from the language to protect programmers from themselves, right? They're teaching to the bottom of the class, right? One of the things I liked when I got my teaching gig was teach the advanced C++ class, and honestly, I wasn't a very good teacher to begin with, and after about 3 weeks, I'd gone from like 34 students down to 8 students the first year. I did that, and I was worried they weren't going to invite me back, and in fact, they were thrilled. They were like, C++, you teach to the top of the class, right? And if someone can't keep up, then that's it. Now all my students stay with me, and I'm worried they're going to be upset. But that's a different story. So the philosophy is, right, we believe it's worthwhile that if you're going to spend your livelihood programming in a language, it's worth investing in learning how to use it, right? And we're going to give you the tools you need to do your job. Okay, right? So on the one hand, you can shoot yourself in the foot with a gun. On the other hand, you won't be bringing a knife to a gunfight. C++. So, right, C++, great and powerful, but you have the responsibility of learning how to use it. I'm going to do one more thing, then we'll wrap, because this will end up being about an hour and 40 minutes. Okay, so can we generalize this lock-free algorithm to create a new, simple, and general paradigm for lock-free coding, right? So one of the that people are concerned with is even with best practices, it's essentially impossible to write correct code with locks. And if you don't use locks, you've risked. And roughly speaking, the reason for that is locking is not compositional, right? Like, I don't know if it's safe for me to acquire this lock without deadlocking if I don't know what everything else in this program is doing, like what locks are held by who called me and stuff like that. So the whole idea of writing large programs is if the pieces are correct, the program is correct. Well, that's not true with locking. So you effectively can't do component-based programming and be confident of not having deadlocks. And it even gets worse in the case of templates, because your template really doesn't understand the locking strategies of the class T in the template, because it's a generic algorithm, right? So there's an important paper called, I don't know if it's written by Hans Bohm or not, but called Generic Programming Requires Transactional Memory. So the question is, can we have a new notion of memory that allows you to program concurrently without risking deadlocks? Okay? So, Hans Bohm wrote Generic Programming Needs Transactional Memory. Right? You clearly got the wrong guy to lecture on memory here tonight. All right. So, we need to roll off soon. So, I'm just going to kind of speed this rather than click the link. But, Armin, you're going to post the slides, right? Right. So, you can click the link to learn more. But the basic idea is well, actually, I don't need that, other than to say C++ committee has released a preliminary draft technical specification to have C++ transactional memory C++. I would say we'll be lucky if we get it in C++ 20, but we might. Okay. It's a pretty major. But let's think about the linked list allocator. Well, it's very low level, so the programmer had to need to keep doing compare and swap. Maybe compare and swap is simulated with locks on your processor and there. So transactional memory says you state the high-level requirements and assumptions that you want to have on this region of code that modifies memory, and you leave it up to the compiler to figure out the best way to satisfy your requirements. Okay? So you can have a block called synchronized, and you're just telling the compiler, behave equivalently to as if there's a global lock on all the synchronized reads. That sounds really slow, but the compiler can analyze the conflicts. Do it too. You atomic block. You've said the requirement. The compiler will figure out things like, this list update isn't going to work atomically. I'm going to keep retrying this atomic block until it works. Cancel on the end just says what to do with the transaction if an exception is thrown. So this sounds inefficient, but modern compilers and processors have many new techniques like speculative execution, hardware and software transactional memory, etc., and the like, that says if you just explain what your atomicity requirements are, the compiler and processor can do all kinds of funky stuff to make things right for you. So the one example is the way transactional memory is usually implemented in hardware and software is the same way databases implement transactions. Do you remember we said that memory can look different to each thread? So what happens is it only makes the memory changes for the current thread, right? Perhaps with like a thread-specific buffer in the memory manager, or, you know, looking up memory locations in a cache and so forth. And only when you decided it succeeds does it actually commit the entire block, just like you would with a transaction. And then the memory management unit will roll back the changes if it turns out some other thread had modified it, the same way the compare and exchange will fail to make the memory change if some other thread is futzed with the list. Yes? Maybe. Remember, the compiler can do whatever we want. It doesn't say what implementation, so maybe at some point it says, at this level of complexity, I'm better off generating a lock. And then it will. So you're much better explaining your needs than the implementation. Think of transactional memory as to concurrent programming what compilers were to machine language, right? So when I said, yeah, we're shooting for C++ 20, and you were groaning, but the fact is, this is like a huge elevation in programming. So I didn't mean you personally were groaning, but yeah, so there's journaling transactional memory, but the compiler can figure out what makes sense, and it can always use a lock if needed, right? So, but it will in a way that will never deadlock. Yes. Yeah, it may do a rollback, or look, it may just serialize everything with millions of locks. I mean, there's a lot of ways it can do it. It often will like speculatively use multiple cores to execute stuff on the same threads in different ways. There's like wonderful techniques coming to light in this. Yeah, I mean, you can't be 100% decoupled from your hardware, but remember, dropping to machine language will almost be never faster, almost never be faster than using a compiler. Once in a while it is, right? Right, with the advances in transactional memory, it's going to get increasingly hard to like outthink the compiler on it. You'll have to use some very high-level strategic knowledge of your program to do that. Yes? So that's that's certainly a very reasonable implementation that you just described. Software transactional memory performance is getting strikingly good as well. So, yes. No, there's for the first version, there's a very restricted subset of the language you can use in an atomic block. Right, so I probably forgot to mention, because I hate that, I think they were too strict on it. So, yeah, basically you're not allowed to do anything that can have a side effect in an atomic block. Right, so it's very, very restricted. I've had some talk with people about it, but like talk is cheap, right? Unless, like I come up with a real provably correct proposal or something, I don't think anybody's going to care. Okay. Yes. Yeah, there's an islock free API that you can call on your atomic operation. It'll tell you if it's atomic in hardware or if they simulate the atomicity blocks. I imagine there'll be something similar for transactional memory, or maybe not, because it could be too determined at runtime and the like. Okay, I think this is a good time for me to go. Oh, let me make one more comment just about threads. Just to close the circle with threads and shared pointers, one important comment here, danger that you should be aware of with shared pointers, is they're thread safe, but when you have no idea when they're going to delete the object they're managing, so you have no idea what locks are going to be held when the object gets deleted. So this is why between like Java 1 and later versions, they moved all finalization into separate finalization threads. So basically, try to never acquire locks in your destructors. And if you need to, take great care or even marshal them over if thread to the actual destruction. So that's another kind of interesting memory / threading thing to keep in mind. Okay, well, thank you very much, everyone. Okay. All right, and thank you, Armin.
And yeah, just quick reminder, if you can return later your badges, that would be great. And there's still some food if you want to grab some and get some home. The more you take, the less we have to store somewhere in the fridge. So thanks for coming.